Section 6.5. We're going to describe and explain the observed trends in atomic size, ionization energy, and electron affinity of the elements. So many properties of elements vary periodically as electronic structure of the elements change. We've seen this from chapter 2, and we kind of reiterated it in the last chapter. These properties govern the chemical behavior of the elements. These periodic properties include size, the radius of the atoms, the ionization energies, and the electron affinities. So let's get into what some of these properties are of atoms and how they change across the periodic table. First one we'll talk about is the covalent radius. This is 1/2 the distance between the nuclei of any two identical atoms when they are joined by a covalent bond. What happens as you move down the group within a periodic table, we're going to get a higher and higher quantum number n. This means that the electrons are added further and further away from the nucleus, and that causes an increase in the size of the covalent radius. This is due to something called the effective nuclear charge. This is the pull exerted on a specific electron by the nucleus when you take into account the electron repulsion effects. It's these electron repulsion effects that make it so that the electrons have different distances from the nuclei, and they're not all just circling the nucleus at the same distance. In our simplest case, hydrogen, there's only one electron, so the nuclear charge Z and the effective nuclear charge are equal. For all other atoms, the electron of interest are partially shielded from the pull of the nucleus by the other electrons present. So core electrons are providing the most of the shielding. So when you wind up So while electrons in the same valence shell do not block the nuclear attractions experienced by others as efficiently. So it's the core electrons that are pushing out, and the valence electrons in this case. Each time we move from one element to the next across the periodic table, Z increases by 1, but the shielding increases only slightly. That's because the electrons are being added only to the valence shell. The effective Z value increases as we move left to right across the period. Here we have an image of the atomic radius, covalent radius, and you can see it's measured as the distance from the center of this nucleus to the center of that nucleus. And here we have a nice picture that's going to show us the atomic radius of all of the elements in our periodic table. Here we have graphed out all of the various radii, and we can see that we see a general downward trend as we move left to right across the period, and then every time we move up a group we have a nice big jump up, and then back down, up, and then over. Ionic radius is analogous to covalent radius, but this is when we're having an ion, okay? And it's not measured as the distance between two ions either. And basically what happens is, if you started with the covalent radius, a cation always has fewer electrons, but the same number of protons pulling on all those electrons. As the electrons are removed from the outer valence shell, the remaining electrons experience a greater effective pull, and charges are drawn even closer to the nucleus. So for this reason, a cation is always smaller than the atoms from which it is derived. An anion always has more electrons and the same number of protons. This results in greater repulsion among the electrons and decreases the effective Z value. This causes the valence electrons to be farther from the nucleus. And for this reason, an anion is always going to be larger. And here we can see some examples with aluminum having quite a bit smaller radius. When you take away 3 electrons, you add 2 electrons to sulfur, and the atomic radius increases quite a bit. So isoelectronic is a term that describes ions or neutral atoms that all have the same electron configuration. So you can imagine that if sodium typically has one more electron than neon, you take an electron away, you make a sodium plus ion, and it will have the same electron configuration as neon. As far as the radius goes, the greater the nuclear charge, the smaller the radius in a series of isoelectronic ions and atoms. So when we make them all isoelectronic with them, the only thing that determines their radii is going to be the size of the nucleus, how many protons they have pulling those electrons closer and closer. So here aluminum would be the smallest, with the largest being nitrogen 3-. Ionization energy. This is the energy required to remove the most easily removable electron from a neutral ion or a neutral atom in the gaseous state while it's in its ground state. And so the first electron that we remove is called the first ionization energy. If we take the resulting cation from that and remove another electron, that's the second ionization energy. And if we did it again, that would be the third ionization energy. As we do that and we do more and more ionizations, it becomes more and more difficult to remove an electron. So every time you remove one, it holds each electron it has a little bit closer. Likewise, removing an electron from a cation with a higher positive charge is more difficult than removing an electron from an ion with a lower charge. And this means that successive ionization energies for an element are always going to increase. The second ionization energy will be higher than, say, the first ionization energy. There's some variations in the ionization energies. Energy is always required to remove electrons from the atoms and ions, so the ionization processes are always endothermic, and the ionization energy values are always going to be positive. What happens is as the size of the atomic radius increases of the atom, the ionization energy decreases. The electrons are being held further away from the nucleus. They're easier to knock one off. Periodically, you're going to see the first ionizations decrease as you move down a group, but increase as you move across a period. Here we can picture that trend. It's always going up as we move across the periodic table, and you'll note that we already know that the ones that are down here at the bottom, lithium, sodium, potassium, rubidium, these are all the ones that we're going to expect to form a +1 ion. And so they have low ionization energies, so it doesn't take a lot of energy to put them into that state. That's why we expect them to do that. Up here we have helium, neon, argon. These are the ones that we would expect to not ever form ions because they have very high ionization energies. And then one like fluorine here, you can see he doesn't want to give up his ions. And we're going to see a reverse trend with another property where fluorine actually wants to take on an electron. Here we have a periodic table showing us all of the ionization energies for all of our elements. There is some deviations in the trends of ionization energies, and this is due to the electron configuration. So if we look at beryllium and boron, the electron that we're going to remove during the ionization of beryllium is an s electron, but for boron it's a p electron. Since the energy of the subshell increases as L increases, this means that an s electron is going to be harder to remove from an atom than a p electron in the same shell. So even though we would predict that beryllium would have a lower ionization energy than boron, because we're removing that electron from the s orbital, it's actually a little bit higher than it should be. Here's an example with oxygen and nitrogen. When we remove one electron from oxygen, we eliminate the electron repulsion caused by pairing the electrons in the 2p orbital. So it actually has a lower ionization energy. Because we're removing this instability of having to pair off electrons, it wants to do that. At some point, there is always a large increase in the successive ionization for an element. This large increase corresponds to the removal of a core electron. These are harder to remove than your valence electrons. An example here is that scandium and gallium both have 3 valence electrons. There's a large increase in the ionization energy that occurs after the 3rd ionization energy. So it'll give up those 3 valence electrons, but it doesn't want to give up that 4th core electron. And here we have a table with some common elements and their successive ionization energies. You can see that there is a steady increase as you move to higher and higher ionization energies. Electron affinity. So electron affinity is pretty much the opposite of the ionization energy. Here we're looking at the energy that happens when we add an electron to a neutral species in the gas state. Unlike ionization energies, this process can be either endothermic or exothermic depending on the element. For some elements, energy is released when the gaseous atom accepts an electron, and that results in a negative electron affinity energy. And for other elements, energy is required, and we have a positive electron affinity energy. It becomes easier to add an electron as the effective nuclear charge of the atoms increases. Electron affinities become more negative across a period. There are some deviations from this trend. And more negative here means actually energy is being released, which would mean that would be the spontaneous direction for this. So when they say the electron affinities become more negative, that means it's more likely to happen. There are some deviations. For the noble gases, they have completely filled shells, and so the incoming electron has to be added to a higher principal quantum number, and so they actually have very low electron affinities because they don't want to do that. For group 2, they have the filled NS shell, and so the next one would have to go into a higher energy NP shell, so they have lower electron affinities. And the same for group 15. Once you have to start pairing off the electrons in those P shells. Here is a table showing electron affinity. We can see it for all of our main group elements here. We can see that some of the higher values are going to be fluorine and chlorine, oxygen, sulfur, and we know these to be atoms that want to form negative charges. So they have these very negative electron affinities.